Good morning, everyone. My name is Kashyap. I represent Thales, Australia, from the Bendigo side. Thales is a multinational company and does a lot of different things. But in Bendigo, Bendigo has a long history of over 75 years. We have done so many interesting things, but what we have been doing recently are the two vehicle platforms, the Bushmaster and the Hawkeye, that has been used by the Australian Defence Force. So for the first five or 6 minutes, I'm going to just talk about how PTC products have helped us to develop the Hawkeye platform. And then I'm going to hand over to my friend Richard, who is going to show you much more interesting things, with all the different analysis and other things that he has been doing using ANSYS LSTI now. Okay. The two vehicle platforms that we currently do design and manufacture in Bendigo. On the left, we have the Bushmaster, and on the right-hand side, we have the Hawkeye, which is the new generation vehicle, that was developed by Thales Australia. Sorry, I think I pressed the wrong one. Yeah, I think. Sorry for that. Yeah, okay. Yeah, and today I'm just going to talk a little bit about how all these products have been very useful in developing our designs and aid manufacturing. So to start with, I'm going to talk a little bit about how Windchill PDM Link has helped us develop the product. Thales in Australia, we have 4 different sites, and with the help of Leap, we have managed to set up replication servers, and we have over 200 connected users that are based over 4 sites to do concurrent engineering. So all our formats and templates are driven from Windchill, and so that we have consistency and standard information that's used to develop the products. We also have other ancillary products or supporting products like MPM Link to do BOM transformation, as in to have a design BOM and a manufacturing BOM, so on and so forth. We also do a few other things like baseline management using Windchill. We have an options modeler where we can use the existing design to create different configurations of the product or create different variants of the product. The proximity filtering enabled interference analysis, this has been a game changer for us. This is using Windchill and Creo view. I'll talk a little bit more about that proximity and filtering and interference analysis when I go to the Creo view part of the presentation. Another important thing we have been able to achieve using Windchill is automatically create some of our post deliverables like step files and DXFs and so on and so forth. So it's no more a manual process. Like depending on the requirements, we can identify what parts need to be provided to suppliers in various formats, and these are all automatically generated by Windchill and kept ready for us to download. And one of the other things that we use Windchill for is to do workflow-driven design release, to take the design through the life cycle, as a concept to prototype to production and so on and so forth. Here, I'm going to just talk a little bit about how Creo Parametric, has been our prime design tool, to develop the Hawkeye platform. So one of the main things, that we do is top-down design. So with top-down design, what we have is basically, the whole product started off with a kind of a layout, where we decided, or, we have been provided all the critical interface information. And then based on that, we generated different initial skeletons. Like, we had a layout, which gave us a starting point of, where, how the product, what are the extents or the boundaries of the products. And then within the product, we have managed to do different skeletons, where we had a skeleton for hydraulics, and we have a overlaid thing for pneumatics. So this way, we know exactly what the space claims are, so that, we don't cross into each other and, create volume conflicts or position conflicts. So by using the top-down design methodology, we have been able to generate the design of, we have 4 different variants of this vehicle here, and everything is driven from a single layout. So top-down design, has been a game changer, for us in the development of this platform. One of the other tools, which have been really helpful for us, is in the HFE area, where, we have used Creo mannequins. There are different mannequins of different nationalities and sizes, and depending on the specification, we deploy the required mannequin to do reach analysis, or, it could be vision cone and various other things. We have also been quite benefited from the 3D cabling and harness design module from, the Creo Parametric, where, we have been able to design the 3D harnesses, and we know exactly, where it is routed, and we have very accurate space claims, driven by Creo schematics, where Creo schematics is more of a 2D layout, and we use that to drive the 3D side of it. We also use Creo model check, where, we can do it's more like a spell checker, if you, for Word, it's a model check, make sure that, we have all the right information, and we don't have anything, that's not desired in the design. What we have also been able to successfully manage is, eliminating the 2D drawings. So almost every model in the Hawkeye platform, has model-based definition. So by using model-based definition, we capture all the critical manufacturing, PMI, product manufacturing information within our 3D models. So that way, it has, like I said, eliminated 2D drawings, in the process. Like I said, we use Creo schematics. So 2D schematics, it will help us to drive 3D models using the logical information from this process. One other, so Creo View, of course, everyone, most of us, you would know that, Creo View is a Creo, it's a part of Creo Suite, and, it uses a lightweight, viewable platform, for design reviews and various other things. We use Creo View quite effectively in the process. Earlier, I mentioned about the proximity filtering in Windchill, which is a kind of a hidden gem, And then, what that does is, if you imagine a harness, going from the, a front of the vehicle to the rear of the vehicle, and you want to see all the different routing paths, and you want to see whether, there are any intended or unintended interferences with other systems. What proximity filter does is, if I go and set a value, say, show me all the components, that are around, say, 5 to 10 millimeter around the subjected assembly, the Windchill will help us filter and provide a configuration, with all the surrounding components. And using that one, I'm going to use that information, within Creo view, and using the interference analysis tool, I can go and check for interferences and clearances, intended clearances, whether, we have achieved, what we were trying to do or what we wanted to achieve. So yeah, and like an example here, when I have when I run the analysis, that's going to show me, what's the interference, how much, what volume of interference, and so on. That way, we can go and fix the issues there. We also use Creo Illustrate. This is more of an activity for support services side of the business. Because of the nature of the size of the product, and with all the different variants, we also have to use the massive assembly license to which helps us to manage bigger viewables. We use Creo View to do design markups, or we use it in the review process, so that we can do markups and provide the necessary feedback for cross teams to do the required changes or the thing. And one other very important thing that we have managed to use by using these products is to re-educate our suppliers. A lot of suppliers were very reluctant to come out of the 2D space. They always wanted drawings, they wanted DXFs. So by using, we have kind of introduced all these systems to our supply base, and now we have been successfully managing them to be with us and supply the thing using some of these products. So yeah, that's all I've got from my side. Thanks for Leap for providing me this opportunity, and I'll hand over to my good friend Richard Smith, who's going to show you more interesting things.
So thank you, Kashyap. So my name's Richard Smith. I work up with Kashyap up in Bendigo in the protection department, I guess. If somebody asks me what I am, I'm a protection engineer. So we look after all things bombs and ballistics and how to design our vehicle platforms for that, which is a really challenging role, but because of that role, we also do an enormous amount of simulation. So we obviously have ANSYS, ANSYS Workbench. We've got a few seats. We use it for all the general things, static, structural. We do some PSD fatigue analysis, or we do a lot of consultancy with Leap. Leap does a lot of good work for us there. Modal analysis for resonance and studies, and rigid body dynamics for kinematic studies. But I'm not going to talk much about that stuff today. I'm going to talk about what really interests me from an analysis point of view, given I'm a protection engineer. So primarily for protection, our load cases are blast simulation, crash loads, rollover, aircraft landing loads, and suspension loads. And particularly this one at the top, the blast simulation. You imagine ours is a protected vehicle, so this is the most important load case. Basically, the entire vehicle is built around this load case. And that demands basically flexible dynamics or explicit codes. So we use ANSYS LSDyn or ANSYS STR. So these events generally are high energy, short time duration, less than 2 seconds. In fact, 1 second is a long time for probably explicit dynamics. They're highly non-linear, loading materials and contact, and they're achieved through pretty big parallel processing. So we have a fairly large HPC to do these analyses. So what are we talking about? Where's my mouse down here? So that's obviously a mine blast on a Bushmaster platform. We conducted that test in, I think, 2012. We conducted that test at 2012. We were testing some of the structural upgrades in the hull at that time. Obviously, a fairly violent event, and so the load case for this is particularly challenging. So how do we design our structures and our internal structures for these kinds of loads? So during an event, we'll have accelerometers. We'll instrument the vehicle. So we've got accelerometers on the floor. That's the front of the Bushmaster. That will give us a time acceleration trace, something like that. We stick it into our big HPC computer, just a few stats on it. We've got 256 cores, blah, blah, blah. So it's a Linux-based server machine. And then what we can do, so this is our post-process signal that we've measured from the actual blast, as I said. We can map that to the rear wheel of the vehicle. And what you see here is a high-speed video of the actual Bushmaster about to blow up. Here's the charge down here. The data from that particular test, as I said, is measured, fed back into the model, and the coloured thing here is the model overlaid with the actual event. So I'll just play that. So you can see here the motion of the model is very similar to the actual blast. Obviously, this turret on top of the vehicle wasn't there in reality, but that gives us the chance to study components like this. Nor was this guy. I think if he was up there, he'd have a sore head. But what this tells us is this reference frame, this acceleration reference frame, is accurate, and to the actual test. Again, he'll be out of luck, this guy. So it tells us then we can, within that reference frame, then we put all of our, so we have one of our major requirements is everything inside the vehicle we have to conform to mine blast, which is nothing's allowed to rip off the wall, become a secondary projectile. So every single thing we put inside the cabin of Bushmaster and Hawkeye, we have to run through these analyses. So in this case, you see some large racks at the back with some masses, radio racks, workstation. And again, things can bend, but as long as we prove they don't break and fall off, that's fine. They don't have to work afterwards. So this is Hawkeye. Actually, this is a really large, complex radio rack in the middle of the Hawkeye. And that was a real challenge to get to work from a modelling point of view and a design point of view. So what we've seen so far is structural considerations. Now, when there's a direct human injury or human-related, we have to do a different kind of analysis. So this is the same blast we saw outside. This is the guy on the inside now. So these are essentially standard crash test dummies, modified slightly. So they'll measure the signal, all kinds of signals, and then we compare it to this table. So this is out of a standard 4569 it's called, but it's a NATO standard that sets out how to pass or fail one of these tests. And basically, the body is broken up into different segments: head, neck, thorax, spine, femur, tibia. And these are metrics for each one of these numbers that these guys measure. So we blow it up, we compare it to this table, and it has to be below each one of these numbers. Without going into the numbers, it's not important, but generally this thing called a DRIZ here is to do with the spinal compression, and this lower floor here, tibia force. So those two numbers are the things that drive the seat design and the floor design, which is the most challenging part for what we do. Getting those two to pass is a lot of work. So in the simulated world. So this is a standard crash test dummy that comes calibrated with the software, with Alice Steiner in this case. So we don't develop this. It's just what they use in the automotive industry. So he's got all the same components as the real Hybrid 3. So we can map, we can investigate any part of his body. And deploying him, so this is neither Hawkeye or Bushmaster, obviously. It's a little pretend vehicle we modelled up. We wrote some papers and we weren't allowed to actually publish using Hawkeye or Bushmaster. So we developed this little pretend vehicle just to show the processes, the simulation process. And in this case, we're simulating the blast itself in a simplistic form. We're getting some local deformation in the hull. And then you can see the dummy is in there. So he's then generating the injury responses in the simulated session. So this is the DRI curve. So that allows us to obviously design seats and floors and all the other subsystems. And that's on a simple vehicle. Now this is a similar thing, but this is obviously a fully meshed Bushmaster. So it's a fully meshed shell, so we can put the charge anywhere on the vehicle. It's got all the right floor plates, all of the mass, so it's massed up. The inertia properties of the vehicle are correct. And you'll see the charge go off under the ground here. Now this is an actual test that we were recreating, and you'll see that in the next slide. We were worried about limiting this deformation in here. We were doing this work with the Commonwealth. So again, it's a big, pretty complex model. Now this is the interesting thing. So this here is the same simulation you just seen, but from a different view. So I've moved the view, and this was video of the exact same blast that we got after the simulation. So what I'm trying to say there is we did the simulation before the test. Now it wasn't until many months later I actually sort of moved these around and I watched this result, and it was quite amazing, the correlation. You'll see the back door fall off about the same time. The wheel. Do that again. There's a guy standing out of that hatch there, which isn't in the model, but it's a really good result. This is Hawkeye. So what we're doing here is this guy stands on this platform here. Actually, it was that rack that you saw before. And we're developing a collapsible platform there. This is the result before that. So again, standing up during a blast is a bad idea in a vehicle. But we were able to develop this platform that crushed down and limited this greatly. That's some leg injury numbers on the right. Back to our little pretend vehicle. This is another method to blast. This is a method called ALE. Probably a lot of people in here are aware of what that is, but basically, from a blast point of view, this simulates the actual soil, the blast products, the fluid structure interactions right through the whole, in this case, through to the seat, and then the dummies involved. So this is the most difficult way to do it, but the most general at the same time. And anyone who's done any of this knows how complicated and how difficult it can be to get to work. There's Luke somewhere. And that's it from me. Any questions?